At this point, some of you may be asking, how do we know what the cross-sectional area of a solid is as a function of x? And the answer is that usually, for this type of problem, we're going to define the solid by how its cross-sectional area is defined. Unfortunately, those definitions get very convoluted, so it just takes practice interpreting them. Here's a typical example that I've put up on the screen. So the example is, find the volume of a solid whose base is the region bounded between y equals 4 minus x squared and where the cross sections perpendicular to the x-axis are squares whose side lies across the region perpendicular to the x-axis. Phew. What does that mean? Here, look where I'm pointing, this is a drawing in the xy plane of the parabola 4 minus x squared. So what we can say is that we're going to draw squares where the side of a square is perpendicular to the x-axis and lies right there. So that green line in the bottom drawing gives you the length of the side of a square. This is kind of convenient because if you look at how this is defined, if the length of the side of the square simply runs from this parabola down to the x-axis, then that means that the side of the square is equal to that vertical distance, which is just going to be 4 minus x squared. That's the top. Remember, we did this with area between curves. We found top minus bottom, minus 0. So that's top and bot. And this just becomes 4 minus x squared. So that's the length of the side of a square. Now let me draw that in here. Let's put in a little tick mark for a particular value x. I can say that at any value x, the square has that side. What I'm drawing here, by the way, I've just drawn the same diagram in 3 dimensions, so I'm going to put in a z-axis reflecting the other direction so that we can have all 3 dimensions and we have space instead of just a plane. So I'm going to take x, put that under the parabola, and we see that we have this green side, like that, and the square now grows in, let's draw it a little better, grows in that direction. So there's a square that's growing out of this base, and its dimensions are very well defined. We know the length of the side of the square, so what we can say is that the area of one square equals the length of its side squared. So that gives us the area of one cross section of this solid that we're trying to draw. So now all we need is the third dimension, but that's fairly easy to do because we know that we're going perpendicular to the x-axis. So these squares grow in the direction of the x-axis, and that's another square I drew in on the other end of this base. And making this a little bit thick so that it looks like a slab instead of just a piece of paper, what we can see is that it has a thickness dx. So we can say that the volume of one cross-sectional slab, I'm going to call each of these a slab, is the area of a square dx. So this is the area of one cross-sectional square, and this is the thickness of the slab. And by the way, notice that area is going to be measured in, let's say, square meters. I know I didn't specify what units, but let's say that we're doing this in metric units and it's meters. And of course, the thickness of the slab, the little tiny bit of direction dx, is just measured in meters. So it makes sense that this whole thing here is going to give you a volume of one slab in cubic meters. The units come out right. Okay, so now how do we find the volume of the entire solid? The answer, of course, is we integrate. We add up all these slabs until we get the full volume. So recall that volume, different color here, volume of the solid is equal to the integral of the area of x dx from a to b. In other words, the cross-sectional area dx. So that's going to be integral from -2 to 2, because we forgot to put these points in, this parabola is going to intersect the x-axis at 2, 0, and negative 2, 0. So you can see that the lowest possible x value is negative 2. The highest possible x value is positive 2. I'll just put those points in here too. And we simply add up all the cross-sectional slabs, which comes out to 4 minus x squared squared dx. And that's the integral that gives the volume. I'm just going to zip through the algebra to solve this. And there we go. And by the way, I hope you noticed that trick that I did, how I was able to simplify the initial integral by recognizing that the integrand is an even function. So if you go back to the video on symmetry, you'll see that that can sometimes help you to solve these, help you to evaluate these integrals.